we are continuing our discussion on the chapter thermodynamics. So in the last class we have studied what is thermodynamic system. System represents an assembly of large number of particles described by thermodynamic variables. Okay, that is called a thermodynamic system, and anything outside the thermodynamic system which directly affects the state of the thermodynamic system is called the surrounding. And we have studied what are thermodynamic variables: pressure, volume, temperature, internal energy, then mass, composition. These are called thermodynamic state variables. Okay. Now we can study what is called thermodynamic process. The process in which there are changes in the state of thermodynamic system is called a thermodynamic process. Okay. In a thermodynamic process, for example, if you consider a thermodynamic system, what is a best example for thermodynamic system? A cylinder containing gas, and the cylinder is closed with a frictionless piston. That is the best thermodynamic system. Okay. And in this thermodynamic system, if there is some change in the thermodynamic variables, change in the state of the thermodynamic variables, for example, temperature changes or volume changes, pressure changes, or mass, composition, internal energy, if any of the physical quantity or any of the state variables change, then we can say that is a thermodynamic process. Okay, thermodynamic process in which there are changes in the state of thermodynamic system is called a thermodynamic process. Now we can study the different types of thermodynamic process: isothermal process, adiabatic process, isobaric process, isobaric process, and quasistatic process. So these are the different types of thermodynamic process. Now we can discuss one by one. First process is isothermal process. The process in which pressure and volume of the system change but temperature remains constant is called an isothermal process. The process in which volume, then pressure, etc. changes but temperature remains constant. That is the main thing. Isothermal means temperature remains constant. Such a process is called an isothermal process. For example, temperature of a substance remains constant during melting. In the last chapter we have studied during melting process temperature remains constant. That means during change of state temperature remains constant. Okay, so during melting at 0 degree Celsius for ice, melting point is 0 degree Celsius. So at 0 degree Celsius ice melts to form 0 degree Celsius water, isn't it? So at the melting point the temperature of the substance remains constant until the whole amount of ice or until the whole amount of solid substance get converted to water, temperature remains water, or the corresponding liquid, temperature remains constant, isn't it? So during melting process temperature remains constant, and hence melting is considered as a which type of process? An isothermal process. Okay, so because during a melting process temperature remains constant. Similarly, during boiling of a liquid temperature remains constant, isn't it? So in that also we have studied in the last chapter. During boiling from which one? From liquid state to steam state or liquid state to vapor state, temperature remains constant as the boiling point, isn't it? So boiling is also considered to be an isothermal process. So during change of state temperature remains constant. So during change of state we can consider that process is an isothermal. Clear, children? Now next example, the slow expansion of gas contained in a cylinder. If a gas is contained in a cylinder and it is closed with a frictionless conducting piston. Conducting piston means it allows the transfer of heat with the surrounding. Okay, let the gas is allowed to expand very slowly. So for expansion energy is needed, isn't it? That energy is taken from outside, from the surrounding. So slowly energy is absorbed from the surrounding and absorbed energy is used for expansion, isn't it? So temperature remains constant. So slow expansion of gas, not the sudden expansion, slow expansion of gas is considered to be an isothermal process. Why? Because for expansion energy is needed and then energy is taken from the surrounding very slowly, isn't it? So the energy absorbed is completely used for expansion, therefore temperature of the system remains constant. So these are the main three examples for isothermal process. During the change of state temperature remains constant. So change of state can be considered as an isothermal process. Then slow expansion of the gas in a cylinder is considered to be an isothermal process. we have the ideal gas equation PV equal to nRT. This equation is called ideal gas equation, where P represents the pressure, V volume, R is the universal gas constant, T is the temperature, and N is called the number of moles of the gas. This gas equation is called the ideal gas equation. Okay. For an isothermal process, how will you write the ideal gas equation? For an isothermal process, we know that temperature remains constant, isn't it? For an isothermal process, temperature remains constant. Therefore, ideal gas equation can be written as PV equals, what is PV? PV equal to a constant, isn't it? For an isothermal process, PV equal to a constant. Ideal gas equation can be written as PV equal to a constant. Why? Because for an isothermal process, temperature remains constant. N and R are constant. Along with that, temperature remains constant. Therefore, we can write PV equal to a constant. Clear? Now, for an isothermal process, how will you write the first law of thermodynamics? We have the first law of thermodynamics, delta Q equal to delta U plus P delta V. That means the quantity of heat supplied is used for increasing the internal energy and remaining for doing work. This is called the first law. Delta Q equal to delta U plus P delta V. Clear? Now, for an isothermal process, we know that temperature remains constant. Now, what happens to internal energy? If temperature remains constant, means internal energy also remains constant, because internal energy depends only on temperature. If temperature remains constant, means what happens to internal energy? Internal energy also remains constant. So, if internal energy remains constant, means what is the change in internal energy? Delta U represents the change in internal energy is equal to 0. Clear? Internal energy remains constant. Therefore, delta E equal to 0. Hence, delta Q can be written as P delta V. So, for an isothermal process, first law of thermodynamics can be written as delta Q equal to P delta V. P delta V means the work done. So, the quantity of heat, or we can write delta Q equal to delta W. P delta V means delta W. So, for an isothermal process, first law of thermodynamics can be written as delta Q equal to delta W. The importance of this formula is the quantity of heat supplied is completely used for doing work. Okay, the quantity of heat supplied to a thermodynamic system is completely used for doing work, because there is no change in internal energy. There are two types of isothermal process: isothermal expansion and isothermal compression. Isothermal expansion means volume increases. That means final volume is greater than the initial volume. Okay. So, we have the work done is equal to P delta V, delta W equal to P delta V. For an isothermal expansion, what is delta V? Delta V is positive. Delta means final volume minus initial volume. So, delta V is positive, and hence work done is also positive. So, during isothermal expansion, volume increases, work done is positive. Work done positive means work is done by the gas. That means the quantity of heat supplied is used for expansion. Okay, from the quantity of heat from the absorbed from the surrounding is completely used for doing work by the gas. Similarly, for isothermal compression means the final volume decreases, gas is compressed. Compressed means final volume is less than the initial volume. So, if final volume is less than the initial volume, what happens to change in volume? Change in volume is negative. That means work done is also negative. Clear? Work is negative, that means work is done on the gas. Work is done on the gas. No, gas is compressed means work is done on the gas. So, during isothermal expansion, work done is positive, work is done by the gas, and during isothermal compression, work done is negative and work is done on the gas. Second type of thermodynamic process is adiabatic process. The process in which there is no exchange of heat between system and surrounding is called adiabatic process. So, here there is no transfer of heat between the system and the surrounding. Okay, that means quantity of heat is equal to 0. That means delta Q is equal to 0. No quantity of heat is transferred from the system to the surrounding or from the surrounding to the system. So, the quantity of heat of the system remains constant, or change in quantity of heat is equal to 0. No quantity of heat is taken, isn't it? Now, examples for adiabatic process is propagation of sound waves in a gas. So, through gas or in a gaseous medium, propagation of sound wave is adiabatic in nature, and the detail of this propagation of sound waves you will study in the last chapter, waves. Okay, how it is adiabatic in nature you will study there. Now, second example is consider a gas enclosed in a thermally insulated cylinder fitted with non-conducting piston. If the gas is compressed suddenly by moving the piston downwards, heat is produced. Okay, so if a cylinder if taken and gas is filled inside the cylinder and the cylinder is closed with a insulating or non-conducting piston, okay, non-conducting piston, and the cylinder as a whole it is completely insulated from the surrounding. Therefore, there is no transfer of heat take place between the system and the surrounding. Clear? Now the piston is pushed downward, the gas is compressed, that means by moving the piston downward the gas is compressed. So if the gas is compressed means heat is produced, compression, heat is produced there, but there is no chance of escaping the heat to the surrounding. Okay, because the cylinder is completely insulated, no? So heat produced cannot escape to the surrounding. Clear? Now what happens to temperature inside the gas? Temperature increases. So this is the best example for an adiabatic process. So if a gas is taken inside a insulated cylinder and it is closed with a non-conducting piston, and if the gas is compressed suddenly, and by moving the piston downward heat is produced, but there is no transfer of heat with the surrounding take place. So what happens to temperature? Temperature increases. Now we have ideal gas equation PV equal to nRT. This is called ideal gas equation, where N represents the number of moles. Now for an adiabatic process, ideal gas equation is written as PV raised to gamma equal to a constant. Okay, this is the ideal gas equation for an adiabatic process. PV raised to gamma equal to constant, and gamma is Cp divided by Cv. In the last class we have studied what is Cp and what is Cv. Cp means molar specific heat capacity at constant pressure, and Cv means molar specific heat capacity at constant volume. And we have studied Cp minus Cv equal to R, universal gas constant R. That relation is called the Mayer's relation. Okay, that you know. Similarly, the ratio of the molar specific capacity, that is called the gamma. Okay, that is gamma, no special name for this gamma. So gamma is the ratio of the specific heats. So ratio of specific heat capacity of at a constant pressure and constant volume, that is called gamma, and gamma is a constant for different gases. Okay, for nitrogen gas, for hydrogen gas, for oxygen gas, etc. Gamma has a definite value, that is a ratio of specific heats. So ideal gas equation for an adiabatic process is PV raised to gamma equal to constant. Similarly, we have first law of thermodynamics, delta Q equal to delta U plus P delta V, or delta Q equal to delta U plus delta W, isn't it? This is the first law of thermodynamics. Now, for an adiabatic process, we know that no quantity of heat is absorbed, no quantity of heat is rejected. So, what is delta Q? Delta Q equal to 0. No quantity of heat is taken from the surrounding, or no quantity of heat is rejected to the surrounding. So, delta Q is equal to 0. So, how will you write the first law of thermodynamics for an adiabatic process? Delta Q equal to 0. So, 0 equal to delta U plus delta W. Or we can write delta W is equal to minus delta U. Clear? So, delta W equal to minus delta U. What does it mean? Work is done by the gas using its internal energy. Okay, no quantity of heat is absorbed from the surrounding. So, using its own energy called internal energy. Using its own energy, what is done? Work is done. Clear, children? So, here the importance of this formula is work is done using its internal energy. Clear? Thus, we know for an adiabatic process, delta W equal to minus delta U, isn't it? So, it can be written as minus delta U means the change in the internal energy, that is final minus initial. Okay, usually delta U is the change in internal energy, means final internal energy minus initial. So, this can also be written as, if you consider this negative sign, it can be written as Ui minus Uf. Isn't it, children? Ui is the initial internal energy minus Uf is the final internal energy. Clear? So, that is work is done using its own internal energy. No quantity of heat is obtained from outside. So, work is done using its own internal energy. Now, for an adiabatic expansion, Adiabatic expansion means no quantity of heat is taken from outside, gas expands. Okay, piston is pushed upward and no quantity of heat is absorbed from the surrounding. So using its own internal energy, what happens? The gas expands. Clear, children? So what happens to final internal energy? Final internal energy decreases because the gas expands using its own energy, no? So its own energy decreases. So final internal energy decreases. Clear? So what happens to delta W? Delta W is equal to a positive value. So work done is positive. For an adiabatic expansion, work done is positive, and here we can say that work is done by the gas, isn't it? By the gas. The piston is pushed up using its own internal energy, therefore work is done by the gas. So for an adiabatic expansion, what happens? Using its own internal energy, it does some work. So what happens to final internal energy? Decreases. Temperature decreases, no? During expansion, temperature decreases because its own internal energy is used for doing work. So its internal energy decreases, that means its temperature decreases. Clear, children? So UF is less than UI, final internal energy is less than initial internal energy. So what happens here? According to the figure, according to the formula, UF is less than UI means delta W is positive. That means work is done by the gas. Similarly, for adiabatic compression. So for adiabatic compression, how will you write? The gas is compressed. Okay, the gas is compressed, the piston is pushed down, gas is compressed. So what happens to temperature? Temperature increases, isn't it? So UF is greater than UI. Final internal energy is greater than initial internal energy, that means temperature increases. So according to the formula, UF is greater means what happens to delta W? Delta W is negative. That means work is done on the gas. So during adiabatic compression, the gas is compressed suddenly. That means what happens to temperature increases, internal energy increases. That means according to the formula, delta W becomes negative. Okay, that's all about adiabatic process. So we have studied two important processes, isothermal process and adiabatic process. Now, third type of process is isochoric process. The process in which volume of the system remains constant is called isochoric process. The process where volume remains constant, that is called isochoric process. Okay. Now example for isochoric process is when a gas is enclosed in a cylinder having a rigid wall. Okay, gas is taken in a cylinder and the cylinder has a rigid wall and it is closed with a fixed piston. Piston, not movable piston, it is a fixed piston. So what happens when the gas is heated? There is no change in volume, no, because it is a rigid one. No, volume remains constant. So such a process can be considered as isochoric. Clear? Now for a first law of thermodynamics, we know delta Q equal to delta U plus delta W, or delta W is P delta V. So delta Q is equal to delta U plus P delta V. Now for an isochoric process, we know that volume remains constant, isn't it? Volume remains constant. So what is the change in volume? Change in volume is equal to 0 because volume remains constant, no? So change is equal to 0. So first law for the isochoric process can be written as delta V equal to 0. So delta Q is equal to delta U. Okay, P delta V, that becomes 0, work done becomes 0. So delta Q equal to delta U. That means here there is no work done. If you give quantity of heat, that quantity of heat is completely used for increasing the internal energy. So here this system or this type of process cannot be used for doing work because there is no work done. Isn't it, children? So delta W equal to 0. So quantity of heat supplied is completely used for increasing the internal energy. Okay, so that's all about isochoric process. Then next process is isobaric process. The process in which pressure remains constant is called the isobaric process. Okay, isobar means pressure remains constant. Now, first law of thermodynamics is delta Q equal to delta U plus P delta V. So first law of thermodynamics actually represents constant pressure. Here pressure remains constant. Okay, so same formula is applicable for an isobaric process, that is again delta Q equal to delta U plus P delta V. So first law of thermodynamics is equally accepted for isobaric process as such. process we have to study is quasi-static process. Quasi-static means infinitely slow process. Okay, quasi-static, infinitely slow. Quasi-static is the process which is infinitely slow process in which the system changes its pressure, volume and temperature so slowly that it remains in thermal and mechanical equilibrium with the surrounding. If the pressure change, volume change and temperature change very slowly and always the system and surrounding are in thermal and mechanical equilibrium. Mechanical equilibrium means if pressure and volume remains constant, that is called a mechanical equilibrium. If temperature remains constant, that is called a thermal equilibrium. Okay, if the process is taking place but pressure, volume and temperature of the system and surrounding remains constant, such a process is called an quasi-static process. It is actually a hypothetical construct. Okay, so it is only an idealized case and it is a hypothetical construct. If pressure remains constant with the system and surrounding means definitely volume or temperature change. If volume remains constant between the system and surrounding means temperature and pressure changes. Okay, so if all the three physical quantity remains constant with the system and surrounding, such a process is called a quasi-static process and it is purely an idealized case. Now, in your textbook, one more process is also given, that is called cyclic process. Okay, if in a cyclic process the system returns to the initial state after undergoing a series of thermodynamic process. So, after an isothermal process, an adiabatic process and so considering so many thermodynamic processes, if the system returns to the initial state, okay, such a process is called a cyclic process. So, it can be isothermal, it can be adiabatic, isobaric, isochoric and so many processes are there, and if the system returns to the initial state, such a process is called a cyclic process. Okay, so cyclic process is the combination of different processes. Cyclic process include isothermal and adiabatic. Cyclic process may include isothermal and isochoric. Okay, so after so many processes, if the system returns to the initial state, such a thermodynamic process can be considered as a cyclic process. So, thus we have studied the different thermodynamic processes, that is isothermal, adiabatic, isobaric, isochoric and quasi-static. Hope you understood the different types of thermodynamic process. Okay children.